Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 34, part C. We are going to conclude our discussion of the bivariate discrete distributions. So last time we talked about the mean and the variance and expectation and even independence. This time we're going to talk about the trinomial and the multinomial distribution. So I need to define some special I didn't realize I'd left some scribbling on this. So let's talk about the definition here of this. We can call it a combination, but it's not really. It's more like a permutation. So n, and then we have x1, x2, and then the remainder, n minus x1, x2. And so that's just going to be the factorial of n over the factorial of x1, factorial of x2, factorial of what's left over. So we're going to define the trinomial distribution, and the marginal of the trinomial, x1, is binomial with parameter n and p sub x1, or you could, if you want to make it easier, p1. That's what I usually do. And x2 is binomial n and p of x2. Then the joint distribution function of x1 and x2 is given by this expression here. And don't forget where x1 and x2 is less than or equal to n, and x1 equals 0, 1, etc., and x2 equals 0, 1, etc. Okay? It's just like a binomial because x1 has to be a binomial, x2 a binomial. So we have p of x1 raised to the x1, p of x2 raised to the x2, and then the remaining probability raised to the remaining number of trials. Okay, so in a manufacturing company, and I will get rid of this real quick. In a manufacturing company, 95% of the company's products are good. They meet specifications. And 4% are seconds, and 1% are defective. Okay? So our quality assurance personnel randomly select 20 items. We're going to let x1 be the number of seconds, x2 the number of defectives. So the rest will be good parts. Find the probability that at least 2 are seconds or at least 2, this is not clear, but at least 2 are defective. So one or the other. So we write it out using notation. Please do that. So I've got x1 greater than or equal to x2 or x2 greater than or equal to 2. I can use De Morgan's law to take the complement of this, and so the complement of x greater than or equal to 2 is x1 less than 2. And x2 greater than or equal to 2, that complement is x2 less than 2, and then I take the complement of the whole thing. And if I have a complement of the whole thing, I can write it as 1 minus the probability of not the complement, right? So the complement of the complement is the original. So 1 minus the probability that x1 is less than 2 and x2 is less than 2. So when x1 is less than 2, I have two ways that can happen. Well, actually, I have more than that. But this is saying that the probability that x1 is 0 or x1 is 1 and x2 is 0 or x2 is 1. So I have actually, 4 ways? 0, 0, 0, 1, 1, 0, and 1, 1. Those are all ways that, well, not 1, 1. We can't do the 1, 1 because that is not less than 2, okay? So x1 less than 2 and x2 less than 2. And so I can have 0, 0, I can have 0, 1, and I can have 1, 0. And I'm trying to think if I need that. So, oh well, I can have 1, 1 because it says x1 less than 2 and x2 less than 2. It doesn't say that the sum, the total, is less than 2. So yes, I can do 1, 1. So I've written out 1 minus the probability that x is 0. So this is, so what I've written here is f of 0, 0. And here is f of 0, 1. And this is f of 1, 0. And this is f of 1, 1. Remember that these are probabilities. And so I've written 1 minus this, and so I've plugged in using my formula, my PMF up here, joint PMF, and I get this value. Please work through this and make sure that you understand what I plugged in where, and make sure that you get that so that you can do this, okay? And now I want to introduce you to the multinomial. And so in this case, this was trinomial. We had 3 categories. Now we have multiple categories, multinomial. In fact, we're going to say that we have k categories. And so each of the marginal distributions are binomial from x1, x2, x3, all the way up to xk. And so they have n, and then p sub x1, p sub x2, p sub xk. And so the probability of x1 and x2 and x3 all the way up to and xk is given by this. I could also write this as n, and I've got x1 comma x2 comma all the way up to xk. So that's, and then, so this, I don't want to say equals there. I'll say that you could write this way if you want, okay? So that's a shorthand way of writing it. And then we have the probabilities. And notice that I don't have a difference here. When we had this, we only had 3 categories, so x1, x2, and n minus x1, x2. It's a little cumbersome, but it's not bad. But here I've got k minus 1, and I'd have to write, for this one, I'd have to write 1 minus p sub x1 minus p sub x2 minus all the way up to p sub x sub k minus 1. That's way too much. So we just let it be p sub x sub k, all right? So now remember that all these probabilities, the p's, have to add up to 1. And all the x's, the different x's, x sub 1, x sub 2, all that has to add up to n. Okay? So let me clean this up a little bit. Okay. So we have to have this true, we have to have that true. And now I want to talk about, just briefly, the joint distribution function, cumulative joint distribution function, so CDF, and talk about some properties. And we won't really do anything with this, but I wanted to expose you to this and just let you have some information. So capital F of xy is the probability that x is less than or equal to x and y is less than or equal to y. So the comma is and, it means at the same time. Okay? Now, as you might imagine, and I don't know why all this scribbling is still here. I thought I'd gotten rid of it. Apparently not. So just like with any other, with the other CDF, the univariate CDF, it has to be between 0 and 1. And just like the univariate CDF, f of xy is a non-decreasing function of x and y. And it's non-decreasing whether x is increasing or y is increasing, either one or both. Okay? And it is a right continuous function in x and y. Both x and y, it's right continuous. With the univariate, it was just right continuous. So we would have, let's say, here, here, and then we'd have a jump, and then we'd have here. And so coming from the right, it was continuous because this point was there. Coming from the left, it is not continuous because if we come from the left, then this point doesn't exist. There's a jump there, right? So this is called right continuous, and all CDFs are right continuous. They may be truly continuous in the case of a continuous PDF, but for discrete, they are right continuous. And this is both in x and y, and I'm not going to try to draw it in 3 dimensions. The limit as x goes to infinity and y goes to infinity of f of xy is 1, the CDF. If either x goes to negative infinity or y goes to negative infinity, the CDF goes to 0. Okay? So it says if this or this. If y goes to infinity, then f of x goes to the CDF of x alone. And if x goes to infinity, then the CDF goes to the CDF of y alone. So that's interesting. Okay. And then 6, we have the probability of x1 less than x2, or x between x1 and x2, and y between y1 and y2. That has to be a positive or non-negative quantity. And there are some implications. I won't go over those for this course, and we'll save this for our continuous PDF. Okay. So don't forget to scan and upload your lecture notes before midnight of the date listed on the course calendar. If you have questions, come to virtual office hours. If you can't do that, email me, but email me a picture of your question and a picture of the problem so I can help you through email. I may not have access to the problem. So please take care of yourself, and we will see you next